Hi, my name is Jaehan Lim. This is a joint work with Chinwei, Aaron, and Chris from Mila. I'm going to introduce a new classification-based training method for unnormalized density models called bijective-contrastive estimation. One way to characterize a random variable is to describe its density. Energy-based models define density functions by exponential of negative potential functions and the corresponding normalizing constant. One important property of EVM is that its parameterization has almost no constraint, and therefore it's easier to parameterize a flexible density function. However, it's difficult to maximize the likelihood of EVM for training. It's because the estimation of log partition function is usually intractable, and generating samples from the energy function is not easy, even when computing a gradient. In order to avoid these issues of MLE, other training criteria has been proposed. For example, noise contrastive estimation, score matching families, and many others. In our attempt to devise new training criterion, we introduce a new classification-based method to learn EVMs from data. Then how to learn a normalized density by classification. Suppose we have samples from two distributions, a data distribution P data and a contrasting distribution Q. We randomly sample a data point from either one of them with equal probability, resulting in the blue curve in the figure. And our task is to determine which one is the source distribution of the observation. For this classification problem, the optimal probability classifier is the posterior distribution of the source given the observation. When you have knowledge of the contrasting distribution of Q, you can plug in the above classifier. And then you can define a classifier that depends only on a model that approximates P data. The learned model in the classifier will recover the data density. This is called noise contrastive estimation, typically when one uses energy-based model in approximating P data. In this work, we define a contrasting distribution in a different way. To create a contrasting distribution, we transform the data using a bijection or invertible function. Again, let's consider a classification problem. Here we produce a contrasting distribution by applying an invertible transformation to data. By using the change of variable formula, we write the density of the transformed random variable as a product of a probability of preimage of x on the source distribution and the Jacobian determinant of the inverse transformation evaluated at x. For this classification problem, the optimal probability classifier is the posterior distribution as in the previous example, but with the density we described in the above. By plugging an energy model in place of P data of x as a P data of preimage of x in the classifier, we define pi. This classifier pi naturally cancels out the normalizing constant. We then learn the energy model to recover the data density by training the classifier. For example, we can consider addition as bijection. The black line describes a data density and the red line correspond to the contrasting distribution, in which we shift the original data by amount of epsilon. The probability of the data point being sampled from the original data is described as blue. Here, one may notice that we can learn the data density by using this one optimal classifier. This is because different density can produce very similar optimal classifiers. Let's see the figure in the top row. The top left is the same example in the previous slide, and the right side depicts another density and its contrasting distribution generated with the same bijection. The optimal classifier on the right side is very similar. Therefore, without knowing any further information about the data, we won't be able to recover the data density from the classifier. On the other hand, the family of optimal classifiers generated by a large collection of bijections will be uniquely dependent on the data's density function. Here, we have the same density as above, but we use multiple bijections to generate multiple contrasting distribution. The behavior of two different sets of optimal classifiers are distinguishable. In other words, with an increasing number of classification problems, there will be less available density that match all of the optimal classifiers of the generated problems. This means we can use the same energy function to solve more classification problems, and this will hopefully rule out all but one density function, which is the data density. As a result, we learn the density by parameterizing all classifier as a functions of one energy and all bijections. We then jointly solve the classification problems. Here, we take expectation over a distribution of bijection. We name our method bijective-contrastive estimation. Then, is any bijection okay here? One of the simplest failure case you can imagine is when bijection T is an identity function. We show that under some mild assumption on the distribution of bijections, the unnormalized density of the minimizer of BC loss must be proportional to the data distribution. The intuition of the condition in the theorem is that as long as the bijections distribution allows to compare enough number of points, then the functional solution of learned unnormalized density will be proportional to the data density. One of the simplest examples is additive transformation following a Gaussian distribution. We show that the additive bijections satisfy the condition of the theorem. Operationally, we can simply sample noise from a Gaussian and add it to data, and then train the classifier using the corresponding loss function. As an example, we run density estimation experiment on 6 2D synthetic data set by minimizing the PC loss with the additive bijections. The top row in the figure shows the density of the synthetic data sets we want to approximate. And the bottom is the plots of the energy function learned by BCE. The result demonstrates that the energy trained with BCE accurately model the 2D synthetic data. Interestingly, when the distribution of bijections and the distribution of their inverses are the same, we can simplify the computation of BC loss. In the original loss on the top, the first term and the second term are equivalent in expectation, and so the loss reduces the next line. For example, consider the additive bijections with zero mean normal distribution. Their inverses also follow the same normal distribution. And instead of generating binary classification problem, we can extend BC to generate multi-class classification problem. Instead of generating one contrasting distribution at a time, we apply multiple bijections to data. We then learn to classify multi-class classifiers parameterized similarly to the binary case. If the distribution of bijection and their inverses are the same, then we can also reduce the multi-class loss into a stochastically averaged version. In the preliminary experiment, we observed that the multi-class BC loss makes the training faster. In other preliminary experiment, we observed that the proposed method did not work well on high-dimensional data, such as image data. We observed that the loss does not provide meaningful learning signals when a generated classification problem is too easy to solve, or a contrasting distribution is too close to the data manifold. For instance, for additive bijection in the image data, the classifiers achieve near perfect accuracy while the learned energy is nowhere near to the true density. We're guessing that this happens when the transform random variable is far from the current energy model. On the other hand, the gradient with respect to their energy can also vanish when t is near identity. In this case, regardless of the shape of the energy, the gradient with respect to the parameter are approximately zero. We aim to address this issue of BC loss in the future. In this paper, we propose bijective-contrastive estimation. We prove that the data density up to normalizing constant is the only minimizer of the BC loss in non-parametric limit. In the experiment, we show that the energy trained with BCE accurately models the 2D synthetic data. We also discussed the difficulty of BCE training in modeling high-dimensional data. Thank you for attending this talk, and I'd like to thank this amazing collaborator. Thanks.